This section of video is going to give you a more difficult example of implicit differentiation and then an application of it. So to start off, just a quick review of our steps. Sometimes we can solve for y, sometimes we can't, and when we can't, we use this process. So first of all, we differentiate both sides of the equality with respect to x. We have to be careful with things like the chain rule or product rule or quotient rule, any of those things. Once we've done that, we get all the dy dx things to the other side, and the stuff that doesn't have a dy dx to the other side. We factor out dy dx, solve for dy dx, and then use it to evaluate the slope of tangent lines in the end. So for this entire example, we're going to look at x cubed plus y cubed equals 6 times x times y. Now that shape is shown over here. This would be something that would be very difficult to solve for y. And so when we say find dy dx, find the derivative, this is going to make implicit differentiation quite useful. So to start out, we take the derivative of all three parts with respect to x. So the derivative of x cubed would be 3x squared. The derivative, whoops, I should really say, let's not say equals here, we'll just say that we're taking the derivative right now. The derivative of y cubed would be 3y squared, but because again it involves y's, I need to put a dy dx, or I'm going to use a y prime just because I think it's a little bit easier to write afterwards. Okay, now that's going to equal the derivative of 6xy. Here's a very tricky part that lots of people forget. When you are taking the derivative of different variables, you have to think of them as different functions. So I really have a function 6x and a function y being multiplied together, so I need to use the product rule. So the product rule was 1d2 plus 2d1, so I'm going to look at writing the first function down. The derivative of y is 1, and then because it's involving a y, I need to use a y prime. Okay, then I write down, remember it's plus 2d1, so the first function was y. The derivative of the first function is, well, 6x is the first function, so that derivative would be the number 6. Okay, so that is our first step with finding the derivative. Now our goal is to get all the dy dx's, or all the y primes, all those parts on one side and everything else on the other side. So here's what I would do. I brought the 6xy prime to this side, so it became negative. I brought the 3x squared to this side, so it also became negative. This became just a 6 times y. And let's see, this chunk up here just moved to the front. So that's the first step that I would do, and then after that we want to factor the y primes out to the front. So the y primes there got factored out to the front, 3y squared is left behind, and minus 6x is left behind. Nothing changes on the right side. And the reason I do that is now I can divide, divide by this entire chunk, and now I'm going to have y prime all by itself. And so now it's divided by that entire chunk, so this would be the derivative. If you notice all four parts there, you can divide by 3, so that's a legal thing to do, and so this would be the simplest form of my derivative. Okay, from there we're going to look at an application. We want to find the equation of the tangent line and the normal line at the point 4/3, 8/3. So 4/3, 8/3, let's see if we can figure that out a second. Be right about there in red. So we want to find the tangent line there and the normal line. And so remember that for both of those we need to know a point, and then we need to know the slope. And so that's going to tell us the slope at that point. So let's start just by thinking about the slope for a second. What is the derivative at this point going to be? We're going to plug in those values and then simplify, and then we'll use that to write out the equations of our lines. So we plug in a 4/3 for all the x's, and we plug in an 8/3 for all the y's, and then we'd simplify. Now this is, you are able to do this without a calculator. It would take a little bit of algebra work, take some time, but it is doable. and I think it's something that you should feel like you have the ability to do. It's okay if you think it would take you forever, but it is something that you should have the ability to do. Now, if you were to plug this all in and go through all that work, you'd end up with a slope of 4/5, believe it or not. So we're going to use this as our slope for the tangent line. So circle a couple things in red. Remember, this is our slope, and this is our point. So as we go ahead and work through our tangent line, the other thing I want you to remember is that our formula for a line, at least if a point slope form, is y equals m times x minus x sub 1 plus y sub 1. Okay, so let's use that for our tangent line. Okay, we would say that y equals 4/5 x minus 4/3. See if I can squeeze that in, plus 8/3. Okay, and now well, first of all, let's talk through that a second. Does it look like the slope right here could possibly be 4/5? Are you going up 4 and over 5 to get to the next spot? I think that that's pretty likely, so that seems to make sense. Our normal line is just perpendicular to it, so the normal line would be going something like that. And for that, we would say that we have y equals, and the only thing that's going to change, perpendicular slopes have to multiply to -1. So basically you put a negative symbol out there, you flip the fraction, and the rest of it is exactly the same. Minus 4/3 plus 8/3. And so far, that's really the application that we've been looking at with derivatives, the fact that they can help us find tangent lines and normal lines. Jot any questions down that you might have, and we will see you in class.